Okay, so let's get right into it. Right now, all around us, the invisible devices that power our digital lives, the switches in our offices and data centers, are constantly talking. They're having these secret conversations, making deals, and making choices that decide if your network runs smoothly or if it all just comes to a grinding halt. But here's a crazy thought for you. To make a network really reliable, you need backups, right? You need multiple paths for your data to travel, just in case one link gets cut. But what if that very thing, that redundancy you built in for safety, was actually the biggest threat to your entire network? And this brings us to what we call the redundancy paradox. We expect our networks to be up all the time. Any downtime is a potential disaster. So we build these extra redundant links between our switches. If one path fails, another one's ready to go. It seems like a perfect solution, but it creates this hidden and potentially fatal flaw, a perfect loop for data to get trapped in forever. So picture this. A computer sends out just one single broadcast message. It's basically just yelling out into the network, "Hey, is anyone there?" Now, in a normal setup, that's fine. But in a network with redundant loops, it's like shouting into a canyon made of mirrors. That one shout doesn't just fade away. It gets bounced back and forth, getting louder and louder and louder with every echo. And this chaos has a name, and honestly, it's as dramatic as it sounds: a broadcast storm. This is that terrifying moment when a network's normally helpful behavior, sending a message everywhere to make sure it's found, becomes completely and utterly catastrophic. And here's how that death spiral actually happens. One message becomes 2, then those 2 become 4, then 8, 16, and it just keeps multiplying exponentially. Now, here's the crucial part. Out on the bigger internet, data packets have a little built-in kill switch, a time-to-live counter, that stops them from looping forever. But down here, inside your local network, Ethernet frames, they don't have that. There's no safety net. They will just loop forever. The result is a network that's so clogged, so full of its own screaming, looping data, that no real work can get done, no legitimate traffic can get through. It's a total shutdown. And the scary part is, it wasn't caused by some hacker. It was caused by the network itself. So how in the world do you get the safety of redundancy without risking a complete meltdown? Well, you need a traffic cop. You need a protocol that's smart enough to see all the different roads and enforce one single safe route. And that protocol, the hero of our story today, is called Spanning Tree Protocol, or STP. The absolute genius of STP is that it lets you have your cake and eat it too. You get to keep all your physical backup cables plugged in, but it creates a single, loop-free, logical map over top of it. It intelligently puts up a road-closed sign on any dangerous redundant paths, but it keeps them in reserve, ready to open up any split second if your main road ever goes down. So how does it build this safe map? Well, the first thing the switches do is pretty cool. They hold an election. They all talk to each other to elect a leader, which is called the root bridge. You can think of it as the boss of the network, the central point that everything revolves around. And once that root bridge is chosen, on that switch, all ports are open for business. Okay, so with the boss chosen, every other switch has one job: figure out the absolute best, most efficient path back to that root bridge. It does this using a system of costs. And it's pretty simple. As you can see here, faster links have a lower cost. So a switch is always going to prefer a zippy gigabit link over a slower one. They do the math, find the cheapest path home, and then they block all the other more expensive paths. All right, so STP is handling the life or death situations, but it's not the only secret conversation happening. There are other protocols out there designed less for safety and more for, well, convenience. Let's meet DTP and VTP, the helpful but sometimes kind of dangerous sidekicks of the networking world. First up, you've got DTP, or Dynamic Trunking Protocol. Its whole job is to make your life easier. Instead of you having to manually configure every single link, DTP lets the switches just negotiate with each other. A port can be desirable, which is the active one, basically saying, "Hey, you want to form a trunk?" Or it can be auto, which is more passive, kind of saying, "Yeah, sure, if you want to form a trunk, I'm down." It's a nice little shortcut. And then there's VTP, the VLAN trunking protocol. Now, this is automation on a much bigger scale. You, the engineer, can set up all your different network segments, your VLANs, on just one central server switch. VTP then takes that configuration and automatically blasts it out to all the other client switches. It can save just hours and hours of really boring, repetitive work. So these tools, they sound awesome, right? They save time, they reduce errors. So why is it that in so many professional networks, one of the first things engineers do is just turn them off? Because when this kind of powerful automation goes wrong, it doesn't just go a little bit wrong, it goes catastrophically wrong. DTP, for instance, is basically a known security risk. Because it's on by default and it's always actively trying to negotiate, an attacker could just plug in a laptop, pretend to be a switch, and trick a port into becoming a trunk. And if they do that, they can suddenly see traffic from every part of your network. That's why the best practice from experts is clear. Turn it off. Configure your links by hand. The danger with VTP, though, is maybe even more terrifying. It all comes down to one little number, a revision number. VTP works by assuming that the switch with the highest number has the most correct, up-to-date configuration. So imagine you're plugging in an old switch you found in a storage closet. If that old switch just happens to have a higher revision number, it will proudly announce its old, wrong, garbage configuration as the new truth. And the entire network will instantly sync to it, wiping out all the correct settings and causing a massive, network-wide outage in a heartbeat. So let's just recap what we've seen here. Redundancy is something we absolutely need for reliability, but it comes with the huge risk of these network-killing loops. STP is that unsung hero, the traffic cop that makes redundancy safe. Then you have the helpful automation tools like DTP and VTP, which offer incredible convenience, but at a really high cost of security and control. The theme that keeps coming up is this constant battle between the power of automation and the critical need for manual control. And that leaves us with a much bigger question, one that goes way beyond network switches. This whole story is really a story about all technology. We want things to be seamless, easy, automatic. But every single time we hand over control, we introduce a risk of some unintended, maybe even disastrous consequence. So the real question isn't about switches at all. It's about us. How do we figure out the right balance? When do we let the machines take the wheel? And when is it absolutely vital that we keep our hands firmly in control?